With IMO's urgent resolution of mandatory measures to address GHG emissions and cut carbon intensity, there's been a strong signal to the market of the importance of swift decarbonization.
Our group DESQ believes that low carbon energy sources such as wind, solar, electric and nuclear energy will rapidly make headway and be adopted in the near future. As the different energy transformations steadily gain momentum, new ecosystems will continue to form. In this presentation, we propose that the integration of renewable energy is necessary to overcome individual limitations of each resource. We will expand more on this idea later through a ship called SEVA. With regards to safety, we maintain that digitalization is the future for ensuring the safety of crew and vessels and can assist in important safety training.
Firstly, we believe that wind power is a viable source of energy. The goal is to convert the electricity created to run generators which are found on the vessel itself. Hence, instead of having numerous tanks to hold the fuel, it could be replaced by the motor which would use to run the generators. There are currently 6 main wind propulsion technologies such as soft, rigid, hull kites, rotating cylinders, and wind turbines that utilize natural wind energy as well as pressure differences in the wind direction as a driving force. Depending on the location, wind could be an abundant source of energy.
Secondly, solar energy serves as a potential pathway to decarbonization by magnifying available energy for solar energy capture. In locations proximate to the equator, solar energy may be of greater asset and investment for ships in this region. The development of new materials, such as perovskites, offers a dramatic increase in solar power output. This suggests an opportunity to move away from traditional installation on flat surfaces and can save space on deck. The success of progress in solar technology has the potential to raise efficiency and push down costs.
Moving on to electric power, there are significant savings compared to running diesel vessels as the maintenance costs are lower. As companies dive into more research in identifying new green energy alternatives, the term electric storage systems seems like a promising route. This technology allows for regenerative energy, which maximizes its potential as an energy source.
Lastly, for nuclear energy, it emits no carbon dioxide and other pollutants. Furthermore, it enables the vessel to run for longer periods without the need for constant refuel. This increases the ship's autonomy and reduces its reliance on fuel prices. This results in reduced mining and transportation effects on the environment. Additionally, uranium is cheaper than current conventional marine fuels. With that in mind, nuclear fusion energy is a plausible source of fuel given the breakthroughs such as the most recent UK-based JET laboratory. While we are aware that fusion energy may be the longest of shots, it will be a diminution of its value to discount the enormous potential to provide immense and steady stream of energy.
Now, as we discuss the advantage of these fuel pathways, we must acknowledge the obstacles that render the pathways demanding these implementations. The common trade-off of these energy sources are:
firstly, zero-carbon vessels are more costly to build compared to conventional vessels. However, we predict that costs will decrease with the increased implementation of these new technologies. Secondly, there may also be opportunity costs that are hidden and they are not directly factored into the installation and operating costs. Furthermore, the risks involved in installing the immature technology may also drive up the capital costs as well as possible uncertainty from investors to fund these new developments.
With regards to wind and solar energy, there may be an increase in distance to follow the meteorological conditions for an optimal journey. The increased length of time per voyage may result in a lesser number of voyages taken within a period of time due to limitation of ships. Moreover, differentiated wind propulsion technologies must be considered for different types of vessels. Similarly, different surface areas are necessary for solar panel installation. This is to prevent interference in cargo handling. The lack of a one-size-fits-all system and specific customization for different vessels raises costs, as different designs and materials need to be accounted for. Additionally, the current effectiveness of wind propulsion is considered slow, at less than 16 knots.
With respect to electric engines, the operational reach for current electric ships is presently restricted due to finite battery capacity. The addition of energy engenders an increase in the number of battery stacks, resulting in heavier weight on board the ship, increasing cost and lesser space available. Lastly, for nuclear energy, safe disposal of radioactive waste generated is very difficult and expensive. Safe storage for used nuclear fuels requires novel designs of ship. New process of redesigning ships would be extensive and arduous. The safety of crew and vessel will have to be prioritized over efficiency.
More crucially, regulatory issues ambitious organizations and companies pose hurdles hindering the implementations. Many countries may also be unwilling to allow vessels with nuclear power to enter their ports. Hence, with the bureaucratic red tapes may also act as a serious implementation to nuclear propulsion.
Moving on to companies pioneering the change. One of the companies pioneering wind technologies includes German company SkyScales and Finnish company Norse Power. They both have vessels that will be equipped with kites and connected to the ship by the ropes.
For solar energy, it is a little challenging for this form of energy to be entirely known as of right now. However, there are existing plans to combine solar energy along with wind energy. Examples include companies based in Japan, such as Eco Marine Power and K Systems, who are trying different configurations to their rigid cells and implementing solar energy to them.
Electric energy, on the other hand, has been going through trials for a longer period. The Japanese company E5 Lab has developed a vessel that's fully run by lithium-ion batteries. They are planning to launch this new vessel named E5 at Tokyo Bay this year tentatively. This lithium-ion battery was supplied by Corvus Energy, a company based in Canada. Corvus Energy uses the same idea of technology as mentioned above, the EAS, to power the E5 vessel. Not only that, we have Keppel, who is also leading Singapore's electric vessel drive. Along with other local organizations in Singapore such as DNV and NTU, they are currently developing electric-powered harbour crafts and infrastructures.
Currently, nuclear power comes into play through small nuclear reactors. They are mostly used in submarines. Lloyd's Register has confirmed the use of 100 nuclear reactors at sea. TerraPower, chaired by Bill Gates, has partnered with nuclear tech company Orano USA to back a new research design for commercial ships. While the public opinion and acceptance could hinder the implementation of nuclear technology into shipping, there is no doubt that the transformation capacity that nuclear power holds.
To sum up our stance regarding the future decarbonization technologies, we conclude that it is highly likely that there will be no silver bullet to shipping's zero carbon transition. However, we believe that decarbonized fuel pathways will be a combination of different fuels, and we do so with good reason. The production of a ship called Seabell combines old and new technology, such as sailing masts with solar panels and a specially designed electric engine. This ship system has the means to capture energy from underwater propellers and a regenerative engine. Captured solar energy will also be stored in the batteries to help drive the ship. Despite her small size as an emerging prototype and slower speeds of 60 knots at the fastest, this innovative merger of different types of energy and fuels could be a highly potential pathways that maximizes renewable energy creation and storage. Most importantly, ships that integrate various carbon-free technologies will be 100% fossil fuel free and will achieve the goal of decarbonization in line with IMO and regulatory standards.
Proceeding to safety measures, we believe new technologies with regards to sustaining and boosting crew safety at sea include wearable systems to combat fatigue monitoring, as it enables continuous, long-term monitoring of biomedical signals in unattended settings with required comfort. There are multiple ways to implement the technology. For example, environmental monitoring can alert crew on unsafe weather conditions, while exosuits can assist in heavy lifting tasks. Thus, wearable technology can be implemented to lower the frequency and severity of injury to crew.
Drones, robots, and unmanned aircraft systems can also be used to minimize crew's exposure to faults and inspections and monitoring risks. Robots can easily access hazardous and difficult to reach locations such as tunnels and storage tanks to perform inspections and collect samples. Safety apps and modernization of safety systems such as the real-time updates of digital logs and offline accessibility of information can assist in tracking crew safety. Research highlights the importance of safety training to reduce crew injury. With the help of apps, safety training can be reiterated through e-learning and can be accessed at sea.
On land, virtual reality, also known as VR, safety training programs give the crew an opportunity to stimulate dangerous working environments and lower risks. VR can also be used for training drills such as entering enclosed spaces. Through practice, it reduces the risk of crew. With regards to vessel safety, we strongly assert the challenging materials of the vessels will provide crucial opportunity to refine characteristics through nanoscale manipulation. For example, the implementation of magnesium or calcium nanoparticles can strengthen wheels, and new anti-corrosion paints as better used to protect the vessels.
Autonomous technology can also help to support crew by providing greater awareness of the vessel's overall situation and condition. They can improve situational awareness through sensors, light detection, pulse lasers, light display resolution, and intelligent software. This means better information display systems to survey both visible obstacles as well as hidden risks. With the growth of data collection and increased research conducted of all relevant interactions between its components and the surrounding environment, autonomous vessels have substantial potential of improving vessel safety.
Ship crew members can apply the System Theoretic Process Analysis (STPA). This safety analysis method is used to treat accidents as a control problem, not just a failure problem. Crew can help prevent vessel incidents by enforcing constraints on component behavior and interactions. This method has been used for safety assessment of systems of varying natures like vessels traffic management, automatic driving vehicles, and offshore supply vessel dynamic positioning.
In conclusion, protecting crew safety and vessel safety are synonymous and of paramount importance. The vessel can safeguard the crew with modern technology systems, while the crew can steer the vessel away from collision. It is imperative to protect both the environment and the safety of our crew members so that we can ride the tide together even amidst gloomy seas ahead. Thank you.